Okay, so this is a review of some of the integral problems that have been done throughout the course. This can include integration by parts, integration using U-substitution, integration using partial fraction decomposition, and the applications of the integral will be in a separate review. So this one right here, if we take a look at this fact right here, 3x to the fourth power plus 1. If we let u equal that expression, 3x to the fourth plus 1, then du is 12x to the third dx. Now the way to check if u substitution will work is if you make this substitution for u, then is du fully covered in the expression if you make the replacement, and is there anything that's not accounted for? So we could say that this is equal to u, so we would have u squared instead of 3x to the fourth plus 1 squared. And we've got to check to see if we have this du term. Du is equal to 12x to the third dx. We have the x to the third and the dx, but we don't have is this 12. But if we multiply it by 12 inside the integrand and then multiply by 1/12 outside, that would take care of that. And then there's nothing left over. If there are things left over that you can't account for using u and du, that's an indication you'd have to probably use integration by parts. But making these substitutions and by multiplying by 12 and 1/12, everything's covered. So this becomes 1/12 times the integral of 12x to the third times 3x to the fourth plus 1 squared dx. So this is 1/12 times the integral. Now we make our substitutions. This term squared becomes u squared, and then 12x to the third dx becomes du. Now the integral of u squared is u to the third over 3, and we multiply that by 1/12, and that becomes u to the third over 36. And we reverse our substitution, and this becomes 3x to the fourth plus 1 to the third power over 36 plus c. And if you're not feeling that rush for time and you can remember, simple integrals like this, pretty easy to check your result. If we took the derivative of this, we should end up with the expression here. So taking the derivative, we would drop the 3 in front. We'd have 3 times 3x to the fourth plus 1 squared, and that's all over 36. And the derivative of this term here will just disappear, but we have a little chain rule inside of here that we need to worry about. The chain rule there would be 12x to the third. And then this 12 times this 3 would be 36. So that would cancel with this 36 on the bottom. You'd have x to the third times 3x to the fourth plus 1 squared, which is exactly what we have here. So the derivative of that checks out. So question 2. I'm going to rewrite this using rational exponents instead of a radical. X squared plus 4 to the 1/2 dx. And again, if we want to try u substitution, we could say that u is equal to x squared plus 4, so then du is equal to 2x dx. So if we let this term equal u, then that's going to be u to the 1/2. Then we've got to make sure that if we substitute for du, that we would have no terms left over. So we already have the x dx part of du, but we don't have that 2. So if we multiply it by 2 here, and then multiply by 1/2, this becomes 1/2 times the integral of 2x x squared plus 4 to the 1/2 dx. Now we have everything we need to make u substitution, and we're using every term. There's nothing left over. So this becomes 1/2 times the integral of u to the 1/2 times du. The integral of u to the 1/2 is u to the 3/2. Now you normally would divide by that exponent now, but instead of dividing by 3/2, we can times by 2/3. So this becomes 2u to the 3/2 all over 6. But then 2 over 6 can reduce to 1/3, and we don't need that 1 there, so it's u to the 3/2 over 3. And then if we reverse the substitution for u, this becomes x squared plus 4 to the 3/2 all over 3 plus c. Okay. Question 3. And we notice this term here. Rather than letting u equal the entire expression there, if we let u equal just the exponent, because what we want to try to get here when using U-substitution with an e exponential term, we want to try to get an e to the u type expression, because those are very easy to integrate. So if we let u equal negative 2x to the 4th dx, then du is negative 8x. Use just the negative 2x to the 4th, the dx is down here, so we have negative 8x to the 3rd dx. So we have the x to the 3rd and the dx. What we don't have is this negative 8. Now, this is a 3. We already have the negative. We can leave that there. If we pull the 3 out and then multiply by 1/8, then we could multiply by 8 inside, and this is everything we need on the inside. We have the negative 8x to the 3rd dx for our du term, and then we could turn this right here into e to the u. So we're going to have 3/8 times the integral of e to the u du. Now the integral of e to the u is simply e to the u, so this is 3/8 times e to the u, which is 3/8 times e to the negative 2x to the 4th, and we add our constant of integration. Okay, question 4. Now quite often we've been able to move numerators up, or denominators up to the numerator to give negative exponents. We can't do that here because it's just this term, x to the 3rd, that has an exponent. If this were in parentheses, x or 3 minus x to the 3rd, then we can move it up. But we can still try a U-substitution, making it equal to the entire denominator. The goal we're going for here is to end up with something of the form 1 over u du. If we can end up with something of this form, then the integral of this is the natural log. So if we let u equal 3 minus x to the 3rd, then du is equal to negative 3x squared dx. Now we have the x squared and the dx. What we now have is that negative 3. So if we multiply by negative 1/3, that allows us to multiply by negative 3 on the inside. And now we have all the pieces we need to use U-substitution. So this becomes the integral of 1 over u du, which is negative 1/3 times the natural log of the absolute value of your u term, which is, so that turns into negative 1/3 times the natural log of 3 minus x to the 3rd. And we have the constant of integration. Question 5, this is a definite integral. So we still find the antiderivative using normal integration techniques. So I'm actually going to turn this into 2 separate integrals. We'll find them separately. So the integral of this the integral of x to the 1/2 is x to the 3/2, and then instead of dividing by 3/2, I'm going to multiply by 2/3, and I'm going to evaluate that antiderivative 1 to 4. Now we're going to add that to the antiderivative here. And the integral of x is x squared over 2, and then again it's going to be evaluated between 1 and 4. So taking this first part here, evaluating this first of all with the upper bound, which is 4, this becomes 2/3 times 4 to the 3/2. Then we minus the same antiderivative evaluated at the lower bound here. So this becomes 2/3 times 1 to the 3/2, which is just 2/3. Then we add that. Over here we're going to have a 4 squared over 2 minus 1 squared over 2, which is 1/2. Now, 4 to the 3/2, there's a couple ways you could do this. First of all, the top number is an exponent, the bottom number here is a root, so 4 to the 3rd power is 64. Then you could take the square root, which is 8. Or you could start with the square root. The square root of 4 is 2, and then 2 to the 3rd power is 8. Either way, you're going to get an 8. And then 8 times 2 is 16, so this is 16/3 minus 2/3 plus 16/2 minus 1/2. So what we end up with is 14/3 minus 15/2. If you were to make these into fractions with common denominators, this is 28/6 plus 45/6. You add those together, you get 73/6. Okay, problem 6, finding the area of a region bounded by the graph, by these two graphs. Now it's not asking you to graph these, and you don't have to solve this, but it would be nice here to have a little visual. Both of these are parabolas, they're quadratic functions. This is a parabola that's facing up, this one's a parabola that's facing down. So just a rough sketch of what's going to be happening here. We're going to have some kind of a parabola like this and maybe some kind of a parabola like that. What we're trying to find is the area between them, like that. So what we need to know, first of all, where do those two graphs intersect? Because that's going to give us a lower bound of integration and an upper bound of integration. So to find out where these two graphs intersect, we have to set them equal to each other. X squared minus 4x plus 3. So collecting all the terms on one side to get it equal to 0, we're going to have 2x squared minus 8x is equal to 0. And then we factor it by factoring out 2x, and then we see from here that x is equal to 0 and x is equal to 4. So this is the lower bound of integration, and this is the upper bound of integration. Now, when this was taught, not only do we have to find the bounds of integration, we need to know which function was the function on top between those two bounds and which function was beneath. Now, if we are looking at the graph, it's easier to tell from a graph. The function that's facing upside down would be the function that's above, and that's this one right here. Now, if we're not looking at a picture of a graph, how can you tell? Well, let's actually call these function f and function g. If you pick a point between the two bounds of integration, 0 and 4, 1 for example, and you evaluate both functions at that point, f of 1 is going to be 1 squared minus 4. That's 1 minus 4 plus 3, which is 0. If we evaluate the same g of 1, we're going to get 3 plus 4 minus 1, which is 6. So evaluating it at the same x value, we get a y value of 0 here and a y value of 6 here, which proves that this function is above because it has a higher y value. So the integral from 0 to 4, we start with the function that's above, 3 plus 4x minus x squared. We minus the function that's underneath, x squared minus 4x plus 3 dx. So writing some like terms, this 3 is going to be canceling with that 3 there. This becomes a negative, and a negative here makes a positive 4x, which will combine to make that an 8x. And negative x squared minus another x squared is negative 2x squared plus 8x dx. So the integral of this expression here, if we think of them as separate terms and just integrate each one separately, this becomes negative 2x to the third over 3. This one becomes 8x squared over 2, which is just 4x squared. And we're going to evaluate that between 0 and 4. So, first of all, the antiderivative evaluated at 4, and we're going to subtract the antiderivative evaluated at 0. So if we plug in a 4 to the third power is 64 times negative 2 is negative 128 over 3. And we add 4 squared is 16, 16 times 4 is 64. So this is the antiderivative evaluated at 4. Now we minus the antiderivative evaluated at 0, but this becomes 0 plus 0, which is 0. Subtracting by 0 doesn't really do much. So it's negative 128 plus 64. Now 64 is just 192 over 3. So if we have negative 128 thirds plus 192 thirds, that adds to 64 thirds. That's the area. Whatever the units are, unit squared, 64 units squared. 64 thirds unit squared, rather. Question 7. This is an example of an integration by parts. Because if we try to do U-substitution, for example, we could say, okay, let's let U equal x, then du would just be dx. So we could try to set this up as the integral, and this becomes the natural log of u. But then we have this x to the fourth term that we can't account for using our substitutions here. We could try it a number of different ways just using simple U substitution, but none of them work because we'd always end up with a term somewhere that's unaccounted for. So this has to be integration by parts, where we have to choose a u and a dv. Now the guidelines for choosing u to choose a term whose derivative is more simple than the term you chose. For example, natural log of x. The derivative of that is 1 over x dx, which is considered to be more simple than an expression like natural log of x. The guidelines for choosing your dv term are to choose a term whose integral is easy to find using normal integration techniques. And you'd have to use everything else left over. So if we've already used natural log of x, then dv would have to be everything else, x to the fourth dx. The antiderivative of that is x to the fifth power over 5. So this turns into the integral then of u dv. Now there was an integration by parts formula. If you're taking the integral of u dv, that's equal to u times v minus the integral of v du. So this turns into x to the fifth power over 5 times the natural log of x minus the integral of x to the fifth power over 5. But I'm going to, instead of dividing by 5 here, I'm going to multiply by 1/5. So that can just be x to the fifth times du. This is the v term here. Now we times it by du, which is 1 over x dx. Now this x on the bottom can cancel with one of these, making x to the fourth. So what we have now is x to the fifth over 5 natural log of x minus 1/5 times the integral of x to the fourth dx. So this turns into x to the fifth power divided by 5 times the natural log of x minus 1/5, and now the integral of x to the fourth is x to the fifth power over 5. That's plus c. Now you notice both terms have an x to the fifth power over 5. So if we factor that out, x to the fifth over 5 you're left with the natural log of x minus 1/5. Okay, question 8. We notice here we have this term e to the x in the denominator. We can move that up to the numerator, and we have the integral of 2x times e to the negative x dx. This is going to have to be another integration by parts. We can let u equal 2x, then du is equal to 2 dx. That means dv would have to be e to the negative x dx. Now the antiderivative, in order to find the antiderivative of this, we're going to have to do a little mini U-substitution here. In order to take the integral of e to the negative x power dx, we're going to have to say, okay, we're going to let u equal negative x, so du is equal to negative dx. We have the dx, but we don't have that minus sign, so we need to multiply by -1, so we can put a minus sign there. So this turns into -1 times the integral of e to the u, which is -1 e to the u, which is -1 e to the negative x. So this antiderivative, negative e to the negative x. So we've set up integration by parts, so the integral is equal to u times v, which is 2x times negative e to the negative x. That's negative 2x e to the negative x minus the integral of v times du. So v is negative e to the negative x, and du is 2 dx. They both have constants here that I'm going to pull out, so I'm going to pull out that negative 2, so I can just have e to the negative x dx. This turns into negative 2x e to the negative x plus 2 times the integral of e to the negative x dx. This plus 2 because of this minus and negative right here. Now we've already figured out what the integral of e to the negative x is. We did it right up here. It's negative e to the negative x. So this becomes negative 2x e to the negative x. Now, right here it says plus 2 times the integral of this, but since the integral of this turns out to be negative, I do minus 2 e to the negative x plus c. Since both terms have a negative 2 e to the negative x, I'm going to factor that out. So if you factor this term out from this first part, you're going to be left with an x. If you factor a term out from itself, you're left with a plus 1. And you have the constant of integration. Okay, question number 9. We can move this term up to the numerator, so this becomes the integral of natural log of 2x times x to the negative 2 dx. So if we let u equal the natural log of 2x, then du is equal to 1 over 2x times the derivative of this inside part, which is 2. 2's cancel, so that's just 1 over x dx. Then dv could be x to the negative 2 dx, so then v is x to the negative 1 divided by negative 1, which just makes that term negative. So then the integral then becomes u times v, which is the natural log of 2x times negative x to the negative 1, so I'm going to put the negative sign there. X to the negative 1 is just 1 over x, I'm going to put that all over x, minus the integral of v du. Now, v is x to the negative 1, which is just 1 over x. Du is 1 over x. So v times du is 1 over x squared. And then a negative sign I'm going to put in front of the integrand here and make that plus. So this is 1 over x squared dx. So this becomes negative natural log of 2x over x plus, now if we take the integral of 1 over x squared, we actually found the integral to that already. We did that over here. 1 over x squared is just x to the negative 2. So it becomes negative x to negative 1. So this becomes negative natural log of 2x over x minus 1 over x plus c. And if we wanted to simplify this, we could factor out negative 1 over x. That becomes natural log of 2x plus 1 plus c. Now question 10, this is going to become an instance where we can take the integral using the partial fraction decomposition technique. So if we just take this and forget about the integral function, 2 over x times x minus 2 in the form of a partial fraction is a over x plus b over x minus 2. If you multiply both sides by the LCD, which is x times x minus 2, if you multiply this LCD everywhere, then on the left side here, the x and x minus 2 are going to cancel with x times x minus 2, so you're left with a 2. On the right side, when you distribute here and here, when you distribute to this a term, the x's would cancel, so a is left multiplying x minus 2. And if you distribute this LCD to this b term, the x minus 2's would cancel, so b multiplies with x. Now, the way this was taught during lecture was to choose convenient values for x that would allow each term here to disappear. For example, if we let x equal positive 2, when you plug that into here, 2 minus 2 is 0, 0 times a is 0, so the a term disappears, and that's what's called a convenient value, because then we'd just be left solving for b. So if x does equal 2, then 2 times b is 2b, and that equals 2, so 2 equals 2b, therefore b equals 1. Now if we let x equals 0, that's going to be a convenient term that will let this term cancel. So then, if this x is 0, 0 minus 2 is negative 2, negative 2 times a is negative 2a, so negative 2a equals 2, so a equals negative 1. So the partial fractions of this expression, now we can write as the integral of 1 over x. Actually, it's a negative. That should be a negative 1 right there. A equals negative 1, so it's negative 1 over x plus 1 over x minus 2 dx, and we can do this as separate integrals. It's the integral of negative 1 over x dx plus the integral of 1 over x minus 2 dx. So the integral here is negative natural log of x, and then the integral of this is the natural log of x minus 2. And we have the constant of integration. Okay, question 11. These are called improper integrals. An improper integral is where one of the limits or bounds of integration is infinity. So the way this was described, and this is section 6.4, I believe, improper integrals. When you're taking an improper integral, it involves a limit. This is going to be the limit as a approaches negative infinity of the integral from a to 0 of x over x squared plus 1. Now, this integral here can be found using simple U-substitution. If u equals x squared plus 1, then du is equal to 2x dx. So we have the x and the dx. What we don't have is that 2, but if we multiply by that 2 here, then we can multiply by 1/2. So this becomes the limit as a approaches negative infinity of 1/2 times the integral of 1 over u du. So this becomes the limit as a approaches negative infinity of 1/2. Now the integral of 1 over u du is the natural log of u. And this is not just this is an integral from a to 0. So now we have to evaluate this from a to 0, and then we take the limit as a approaches negative infinity So we have to unsubstitute for u in order before we can evaluate the upper and lower bounds. So this is the limit as a approaches negative infinity of 1/2 of the natural log of x squared plus 1. That's from a to 0. So it becomes, first we evaluate the antiderivative of 0, so this is the natural log of 1. Now we minus the antiderivative evaluated a, this is the natural log of a squared plus 1. And the whole time we're taking the limit as a approaches negative infinity. Now the natural log of 1, that's just 0. The logarithm of 1, any logarithm, natural log, log base 2, any logarithm of 1 is 0. So we're taking the limit now as a approaches negative infinity of negative natural log of a squared plus 1. Now, if we plug in values of a that are approaching negative infinity, and we square them, then it becomes positive, and then we're adding 1. So these values inside of the natural log are getting increasingly larger and larger and larger and larger and larger. This is an example of a limit that it diverges is what it's called. Therefore, the limit does not exist. This goes to infinity as a goes to negative infinity. Since the limit does not exist, it's not possible to evaluate this integral. So we say it diverges.